Hello and welcome back. In this unit we're going to be looking at center of mass and torque as well as some rotational equations. Today I just want to, or in this video I just want to get into center of mass, and then later we'll get into torque. This is in center of mass and torque has a lot to do with whether or not things balance. This is known as Balanced Rock. It's in Moab, Utah, which is a really cool place. I recommend going to see Moab sometime, see Arches National Park, and some other stuff. It's pretty cool. I've got a picture of me right down here. As a matter of fact, I don't know why this isn't a picture of me right here. So anyway, first off, real quick, the axis of rotation. When something is spinning or rotating, there's a point about which every other point on that object is spinning around. Okay, it's an imaginary line going through that object where every other point is spinning around, and that's known as the axis of rotation. The points on the axis of rotation don't appear to be moving at all. They're stationary. So when we throw an object in the air and give it a spin, the axis of rotation for some simple objects will just go right through the middle of the object. So for a block of wood, rectangular, it just goes through the center of the object. If we throw something like a hammer in the air, it doesn't spin around the middle of the object. So if this was the middle of the object, it's not spinning around that point. It's spinning about a point closer to the head of the hammer, and that is spinning about what's known as the axis or the center of mass. Objects naturally spin around their center of mass, and for symmetrical objects that are uniform, the center of mass just lies in the dead middle of the object. For an object which has got such as a hammer, which has got a hollow handle which is light and a solid dense hammerhead, that center of mass gets shifted towards the area that's got more mass. Okay, so there's more mass in the head, so the center of mass gets shifted away from the center towards the heavier head. As I said before, if objects are symmetrical and uniform, by uniform I mean they're made of the same stuff all the way through, then the object just lies in the middle. So you can draw lines of symmetry, and if you can draw two lines of symmetry, the axis of rotation will lie at the intersection of those. If you can draw one line of symmetry, the center of mass will lie along that line somewhere. But here we've got a triangle. It's not. I can't draw a second line of symmetry. It's going to be shifted more towards the weightier base and away from the lighter tip. If we had an object that was a bar made of half lead and half much lighter plastic, I could draw a line of symmetry down through the object, and I know the center of mass would lie somewhere along that line. And it's going to be shifted towards the more heavier lead and away from the much lighter plastic. So anyway, if we had a baseball bat, where is the axis of rotation going to be, or the center of mass going to be for this baseball bat? If this is the middle right here, where the L is pretty much, it's going to be shifted more towards the heavier end of the bat. So it might be more towards the end of this oval or somewhere, maybe even down there. We could throw it into the air and see, about which point it rotated, and that would tell us what where the center of mass was, because we would just look for the axis of rotation. So if we've got a boomerang, where might the center of mass for this object lie? Well, it looks like we can more or less draw a line of symmetry down the middle of it. It looks pretty symmetrical, down through the middle. Not perfect, but it's pretty close. And so it would lie somewhere along this line running down the middle. Now, is it going to lie up here? No, because there's all this mass down here that's drawing it down. So it'll end up that the axis of rotation, the center of mass, won't even be on the object in this case for a boomerang. And it will rotate around this point if you throw it in the air and give it a spin. When you're talking about the center of mass, you can't just say that there's the same amount of mass to the left and to the right of it. And you know, in some certain situations that'll be the case, but not in a lot of situations. So where would that be in this case? Well, that would be right here. Okay, where I've got half a kilogram to the left of this and 1.5 kilograms to the right. This is not where the center of mass would lie. If you could kind of get an estimate of where you think this might be. So here's my 1 kilogram object tied by a massless stick or string to this 2 kilogram. You probably figure it's going to lie somewhere in the not exactly in the middle, okay, but more towards the 2 kilogram. Okay, so the actual center of mass, would lie right about here. We're not going to get into calculating the center of mass. We're just going to get into real, rough approximations, and I just want you to be familiar with the term. But there is a balance that goes along with this. So if this is my center of mass, I've got 2 kilograms 1 meter away from this, and here I've got 1 kilogram 2 meters away. So when you multiply the distance times the mass, you get equivalent on both sides. So, but like I said, we're not going to get into calculating that in this class. So where's the center of mass with the sun and all the planets? So let's say we've got a hypothetical solar system here. It's not going to be directly in the middle of the sun. It's going to be off to the side a little bit. If the planets are lined up right like this, it's going to be off to the side a little bit. So when the sun is not going to spin like this. It's going to wobble a bit because of the center of mass. And you can think of it as the planets are pulling it and causing it to wobble. So now, does the center of mass stay constant? No. Okay, the center of mass is constantly changing of the solar system. So the wobble of the sun is constantly changing. So let's look at the center of mass before and after an explosion. And we've already kind of covered this a little bit, so we'll skim through this. Here I've got a firecracker. My center of mass would lie somewhere pretty much in the dead middle of the firecracker. Okay, let's say it explodes into 2 pieces. Okay, what's happening to that center of mass? Okay, well, the center of mass is staying right where it is. It's staying right in the middle of those 2 equal halves. So the explosion did not cause a change in center of mass. So if there's no outside forces, the center of mass is based on conservation of momentum. Okay, so the center of mass stays put. Okay, if the fragments are different sizes, so this is like our 2 kilogram object and our 1 kilogram object. Okay, the center of mass is still going to stay put because it's going to be closer to the 2 kilogram object than it is the 1, but the 1 is moving faster, so it's always further away or twice as far away. So the center of mass stays put. So explosions don't affect the motion of the center of mass of an object. So another example of center of mass is, let's say we're looking down through the top of a washing machine. So you're above a washing machine looking down, and these are your blue jeans or whatever that you've got about to go into spin dry. And this is the center of the machine. This is that pole that goes up in the middle of it, where it's trying to rotate about, or where it should rotate about. So my center of mass is right in the middle. So if I go into spin cycle to spin the water out of the clothes, okay, the center of mass where it naturally wants to spin is right on the axle. And so I get a very, very smooth rotation. There's no vibrations. Okay, but if some of your clothes get wadded up to one side, okay, which can happen if you have bulky items like comforters and big things like that, that'll cause your center of mass to get shifted off away from the center of it. So rather than rotating smoothly like we've got here on the left, it'll try to rotate like this, and it'll cause it to vibrate. So if you've got a front loader, then you're looking at it just as you would from the front of it. So again, it's trying to rotate around that center of mass, and that's not what the machine wants to do. Okay, we've already kind of covered that. We've covered that. We've covered that. Okay, and we've covered that. We've covered that. We've covered that. Okay, the center of mass is really important for a bunch of different reasons. If you're designing buildings and or a lot of different things, we know it's the point about which an object naturally wants to rotate. But there's another reason. If you've got a stick like this, so we've got a meter stick, and we want to calculate where this is going to balance, I could look at every single atom, okay, and calculate the force of gravity on every single atom, but that would get really, really, really boring and cumbersome. I don't want to have to calculate it. I want to consider the object as a whole, and what you can do is you can pretend that the center, all of the weight of the object is acting at the center of mass. Okay? And when you do so, technically it's called the center of gravity, but center of gravity and center of mass we'll use pretty much interchangeably. You can pretend like the entire weight of an object is at the center of gravity, which we're always just going to place in the middle of an object when we do math with problems. Okay, we're not going to have like baseball bats or anything like that where you have to estimate the center of gravity. We're going to deal with uniform objects. So you can pretend like the center of gravity, or all the gravity is concentrated at the center of gravity. So when you put a balance point under the center of gravity of an object, it will balance. Okay. So there's a really, really easy way, other than just throwing it into the air and trying to figure out what point it's spinning around. You can just balance it on your finger, and your finger will be in line with the center of gravity, the center of mass. Okay. Now, what would happen if I hung some mass at the end of it? What's going to happen? Okay, that center of gravity is going to get shifted over to the right, and it's no longer going to balance. Okay, that's all I really wanted to